Okay, so we're going to talk now about logistic regression, and I'm not going to get too into this because it gets pretty complex pretty quickly. You'll have a little bit of it on the homework, um, but um, but I just sort of really want to introduce the concept to you and then get you used to interpreting the data. So the fundamental math underneath of it, don't worry about at this point, and just be able to interpret the data and understand when you use logistic regression. And as I've sort of said throughout, like this is just really the basics, and then you can do further investigation if you need to, say, run logistic regression later in your career. So it's just an introduction to logistic regression. So before we're advancing, I just want you to pause this video and um, tell me what types of questions that are answered by regression, multiple or linear, whatever we've been doing so far. So go ahead and pause it and write them down or think about them. Okay, so these are some of the types of questions. We've talked about this. How does each variable affect the outcome? How do the variables affect the outcome in relative importance to each other? So when we looked at those standardized beta coefficients, which one influences the outcome more than the others? And then what is the magnitude of that effect? How does each predictor influence the magnitude, the value of the outcome? Is it a big increase? And that's when we looked at those unstandardized beta coefficients. That's the increase in y in terms of the increase in x. So those are the general types, and this is the same kind of questions we're going to ask with logistic regression. The only thing that's different is logistic regression is used when the outcome variable is discrete, categorical or binary, dichotomous, a yes or no, disease, no disease, a level of something. So there's different levels of obesity. There's non-obese, obese, morbidly obese, etc. So those are different levels. So that could be used. So the outcome variable is discrete, categorical, continuous, whatever, categorical, dichotomous. The explanatory independent variables can be either. They can be discrete or continuous. So the same with linear regression, you could have your independent variables can be either one. With logistic, your outcome has to be discrete. So because we're using those discrete variables and we don't have a continuous variable as our outcome, we're answering the same types of questions, but we're answering them slightly different. So instead of looking at how does each variable affect the outcome, we want to model the probabilities of a response variable as a function of the explanatory values. So we're trying to talk about the probability of somebody being in one category, someone having the disease, not having the disease, as it relates to those explanatory variables. We want to describe the difference between individuals in a different response group. So for example, for the first one, model the probabilities of a response variable. If we want to look at college admittance, the first one we want to see the probability of being admitted to college as a function of gender. So what's the probability of someone getting into school, being admitted, whether they're male or female? Admitted is dichotomous, so is the explanatory variable. For the next one, describe the differences between individuals in a different response group based on explanatory values. We're going to describe the difference in our being admitted to college example. There's two different groups, students admitted or students rejected. So we're trying to describe the differences based on gender. So what are the odds of being female and getting in? What are the odds of getting rejected given that you're a male? And then The last one, to predict the probabilities that someone will fall into a response category as a function of the explanatory values. So what is the probability this student is admitted given that she's a female? So all those are just sort of examples of same types of questions. We're just trying to describe the outcome using explanatory values. So describe whether you get into school or you don't, the probability of that occurring based on those explanatory values. So let's cover this through an example. So if you're a researcher for the Affordable Care Act, you want to determine what's the relationship between a person's credit score and the likelihood that they'll access the marketplace, which is that public insurance through, or what's the likelihood that they'll have that public insurance through the marketplace, or if they'll be privately covered. We want to see that relationship based on credit scores, because credit scores is an easy measure. I can access credit scores through a credit website, whereas I can't necessarily access people's insurance information. That's private, it's covered by HIPAA. So I might want to just get big data to see what's the relationship so that I can make predictions, see what's the probability that someone's going to use public insurance versus private, all those things we just talked about. So we get a data set of 1,000 people. We ask them what their credit score is, and then whether they're privately insured or not, yes or no. So our outcome is dichotomous. And we want to find these are the kind of data we can get from using logistic regression. So we can develop a model of the probability and odds that a person will be privately insured for a given credit score. So if somebody comes into my office with 500, I can say in the probability or odds that they will have private insurance. I also can discover what credit score results in a 50% probability of being privately insured or a 75% probability. If I want to know, the 75th percentile for people that are privately insured, what's the credit score that cuts those two off? Those are all the things we talked about during probability. We can use logistic regression to figure those out. If I want to input a certain credit score and determine the odds that they'll be the odds or probability that they'd be privately insured, I can do that. Determine how an increase in credit score will affect the probability of a person being privately insured. So what happens if you increase your credit score by 100? What does that do to the probability that you are privately insured? So this is what your data will look like. We have our credit scores, and then our dependent variable, our outcome, is insured 0, not privately insured, 1, privately insured. So it looks the same. We have all these different people. We had 1,000 in the sample. Then we get the insurance. So if I just graph these, when we looked at linear regression, we started with that scatter plot. If I go through and I use the credit score as my explanatory value, and I look at my dichotomous value, it doesn't look like a scatter plot that we can draw a best fit line to. All the values that are privately insured are going to be up here, and all the values that are not privately insured are going to be down here. They might be clustered, and we can kind of see sort of a relationship that as a credit score, the higher credit scores are focused here in the privately insured, and they're a little bit lower in the not privately insured. But we can't just draw the straight line. That wouldn't represent. We'd have a lot of error associated. We'd have a large sum of squared errors. So we wouldn't be able to use a linear relationship. So we have to figure out a different relationship, and that is that logistic regression relationship. Well, and going back to this table, the reason that these don't fit a logistic or linear relationship is because we're talking about probability. We're talking about odds. We're not talking about a continuous outcome. And that doesn't allow us to use that normal curve, that continuous normal curve, because there's two clusters that doesn't have the nice bell-shaped curve that we're used to when we're using parametric normally distributed standard regression analysis. So, like if you think about it, the binary data does not have that normal distribution, and that's one thing we need for linear regression. The predicted values are based on probabilities in this case, so that doesn't allow itself really for a linear regression either. And probabilities aren't always linear in nature. I mean, if you think about the probability of someone getting the flu, we have it U-shaped, where young people are more likely and older people are more likely. So the probability doesn't function in a normal distribution. So we have to come up with something different, which is that logistic regression. So we work to model the probabilities of an event occurring dependent on the input variables. And we estimate the probability that an event can occur or won't occur for a particular independent variable value. So if I plug in a value, what is the probability that the outcome will occur? We predict the effect of independent variables on a binary response, a binary or dichotomous or categorical. We classify the observation by estimating the probability that an event will occur, that an observation is in a particular category. So estimate the probability that somebody is in the privately insured if they are of a certain credit score. So again, those are some examples of how we use logistic regression. Real quick, I just want to kind of remind you of a few things with probability. So we have our probability, which is the outcome of interest over all the outcomes. That's our equation. The number of red cards in an entire deck. The number of people of a certain height over everybody. The probability will be related to that difference. And then we can also calculate the odds, which is simply the probability of one occurrence happening over the occurrence of another, the probability of the occurrence not happening. So if I want to see the odds of developing disease, I'm going to see the odds of developing the disease over the odds of not developing the disease. Remember that probability, 1 minus the probability of something happening is the probability of it not happening. The probability of it not happening. So we have the odds, which gives us the relative probabilities, the probability of something happening over the probability of it not happening, all the other options. Probability of somebody being in the first year of college over the probability of them being in their second, third, or fourth year, however you want to work that. And then we can get that odds ratio, which is the ratio of the odds of one event occurring over the odds of another event occurring. So what are the odds ratio? What's the odds of somebody that is 20 getting the flu over the odds of somebody that is 75 getting the flu? So you can see the relative odds of two events happening. So those are some quick probability review. And I'm going to stop there and start a new video, and we'll get more into logistic regression.